So, good morning, dear learners. This is Finite Element Method lecture series 3. So, this is the continuation of Introduction to Finite Element Method. So, and now I'm going to continue with the new lecture. So in our previous lecture, we tried to see different methods applied in finite element modeling and the procedures that most finite element method used. And I briefly explained the introductory part in last two lectures. So let me continue with the next topic. So idealization is one of the finite element method, discretization, finding proper solution, and then the process will go like this. Physical system that the continuum will be considered, then mathematical model, then discretize the model, that means finite element machine, and the solution for the discrete solution will be made. Then solution errors that recycling the process will come, like discretization plus solution error. Again, when we come to here, modeling from discretization plus solution error. So these are some sorts of errors actually. From here to here, we have only solution error. If we go from here to here, we can see discretization error plus solution error. And then from the very beginning to the last, what we can see is the modeling error, that when we are considering the problem domain, we may make some mistake on that. Again, when we are making discretization, there may be some error. And then at the solution step, there may be some error, so that these things are coherent in finite element modeling. So let's take some example, which is helpful to discuss. Let us take a rectangular cross-section bar, which is subject to this axial load P. That P is acting in longitudinal axis. So we can represent it with this 2D representation. Okay, so just taking some appropriate position, U of x, that the axial rigidity of the material EA. EA implies the axial rigidity, the cross-sectional area of the cross-section already represented here. So these are some quantities which are expectably in this modeling. So x is the longitudinal bar axis. The differential format D, this bar, the bar format, d of dx, u of x, that axial displacement, q of x, distributed load. Look, this is q of x. Again, L is the length of bar, E is the Young's modulus of material, A is cross-sectional area, EA is axial rigidity, strain E. E is the strain du dx, that is U bar, infinitesimal axial strain. Again, sigma is equals to E, that axial stress, P, which is sigma times area, that internal force. So these are some of the parameters in most FEM calculations. So let's come to the strain energy. According to Hooke's law, stress is directly proportional to strain in elastic region. This works only in elastic region only. Actually, material will exhibit non-linear behavior beyond the elastic region. So this Hooke's law does not work through in that region. So that So based on Hooke's law, sigma is equals to Young's modulus of material times strain. And the strain is the change in displacement over the displacement in the x. So du over dx, that is strain. So the strain energy is given as half sigma x, half sigma e. That is the area under stress strain curve. I can put that graph. Sorry. Okay. So this is stress strain diagram. Sorry. This is stress. This is strain. Then this is the linear elastic region. So the area under this curve is called the this area, which is called strain energy. So integrating over the volume of the bar, this strain energy per unit volume is given as half sigma integral of sigma in the volume and sigma E strain and dV. So we can use this integral form for the length of bar, okay, from 0 to L. Okay, sigma is equals to here sigma is equals to force over area, stress is equal to force over area. So and here volume is equals to area times x. Volume means area A times dx. Okay, so area is taken from here. So finally, it is when we substitute in the place of sigma p over a and dv, which is equals to a times dx, then we can get p times strain times dx, and which is again represented with ea u prime. That u prime is the du over dx. This u prime means du over dx. Du dx. That is strain. Okay, and here also u prime. That is also the strain. Strain. So this is the representation of strain per unit volume. Okay, so this is the representation. External energy. So due to applied external load like P at the end or Q, that the distributed volume, that distributed load. So due to those loads, Q of X and P, it is not Q, sorry, it is just, sorry. Here P, here it is Q of X, so that that is not, this is P, not Q. Yeah, this is can be included in Q, yeah, okay. So external energy, W, is given as Q times U, that the deflection U times dx from 0 to L. So the total potential energy functional is defined in terms of W and U. Okay, so in terms of strain energy and in terms of the external energy or work potential. So the total potential energy functional. It's not function, but functional. The unknown strain function U is find by minimizing the TPE function, the total potential energy functional, described phi is equals to U minus W, or phi as a function of U of X, which is equal to strain energy minus the external work. And we can represent it with the help of weighted residual method. So the class of differential equation containing one dimensional can be described in terms of the differential operator L of U. So L of U, which is equals to d over dx times p of x, then du dx, this strain, plus z of x u, which is equal to q of x. In the interval of 0 to 1, that is 0 to L actually, for in our case. So u of x at x is equal to 0 is equal to u of L at x L is equal to 1, which is equal to 0. So L of u is the differential operator in this case. So L of u, the differential operator minus q, which is equals to 0, implies that we are minimizing the error function. So this is a minimized error function. So multiplying this by weighting function v, or somebody can use it with w, weighting function w, and integrating over the whole domain, we can get this thing. Okay, this is the weighting residual method application. So integrating it from 0 to 1 or 0 to L for this case, which is equal to 0, means the residual is equal to 0. For the inner product to exist, it must be a square integrable. Therefore, the weighting function should be the second order, that in the domain of 0 and 1. And equation 2, this equation is called the variational form. This equation is called the variational form. So the next step is approximating the function, that appropriate solution. So we are estimating the solution. We can use U for the approximate solution. Let U of x is equal to U of x, that considering the hat function, that Cj pi j of x, summation of j from 1 to n, Cj pi j of x. And in the same form, the weighting function also approximated as v of x, which is approximately equal to v of x, which is equal to summation of j from 1 to n. Somebody can take it as I from 1 to n, and di psi I x. So this pi j and psi j are the functions are of the choice and are meant to be suitable to particular problem. Okay. So we can sometimes use the sine or cosine function in this case, and which satisfy the boundary conditions, and hence it could be a good choice. So U is called trial function. This U is called trial function, or it is approximation function, that displacement function actually. And V is called the weighting function or test function. Okay, this was weighting function. So weighted residual method as the differential operator L of U is second order, that is U is an element of C square, that implies U is an element of C square within the domain of 0 to 1, or it can be 0 to L. And therefore, we can see U as an element of finite dimension subspace of the infinite dimensional function space, C square of 0, 1. So U is an element of subspace of infinite dimension. And in the same way that V is also in infinite dimension. So replacing V and the U with respect to V and U becomes VR, which is equal to 0, for all V, an element of infinite dimension. And R of X, this is called residual, which is equals to the operator L of U minus Q, which is considered is equals to 0. So R of X is called the residual. The vanishing inner product shows that the residual is orthogonal to all function B in the test space or in the weighting space. So substituting the weighting function B of X and into this, we can get which is equal to 0. So this error minimization, this is called, and hence summations and integrals we obtain. The summation of d j psi j of L of U minus Q is equals to 0 for all dj, which is 1 to n. As the inner product equation is satisfied for all choice of V in Sn, the above equation has to be valid for all choice of dj, which implies that psi j of L of U minus Q is equal to 0 for j 1 to n, that based on the number of unknown. Galerkin method. So one obvious choice of psi j would be taken it equals to pi j. This choice leads to the Galerkin method. So instead of psi, just pi j, L of U minus Q is equal to 0. Okay. This form of the problem is called strong form of the problem. So our aim is to make it to the weak form. Okay, so strong form cannot easily solved, so we have to minimize it to the weak form. So because the so chosen test space has more continuity than necessary, therefore it was for this and other reason to convert the problem into more symmetrical form. This can be achieved by the integrating by part. So after integrating the part, the problem integrating by part, finally we can get the weak form of solution, which can easily be solved. So let us remember the initial form of the problem. This is the initial form of the problem. That is L of U equals to Q of X, which is equal to d over dx, P of x, du dx, plus z of x times u. This is the initial, with the interval of 0 to 1. That is the initial problem. This is the boundary condition. Then V L of U minus Q, which is equals to integral of from 0 to 1, V minus P of U, this U prime means du dx. Okay, again, prime here, plus Z of U minus Q. So this Q comes here, minus Q dx. Integrating by part, we can get this equation. Okay. We can get this equation. And the problem can be written as A of u vu, which is equals to integral of 0 to 1 b prime pu prime plus vzu dx. So actually, after integrating by part, we impose the boundaries here. So this is actually called the bilinear form of that A VU is called the strain energy, or in the bilinear form actually. So that bilinear form, and now let's come to the solution space. Now that derivatives of V comes into the picture. V needs to have more continuity than those in L space. As we want to keep symmetry, it is appropriate to choose the function that produce boundary values of A of u, comma u, which is the integral of 0 to 1 pu prime, the whole square, plus zu square dx. So as p and z are necessarily smooth functions, the following restrictions is sufficient. So that from 0 to 1, u prime square plus u square dx. So the function obeying this rule obtained to the so-called subloop space, and they are denoted by H1. We require V and U to satisfy boundary conditions, so we do not denote the resulting space as H01. So this is the linear system of equation. Finally, this is the solution. Now takes the form that A of VU, which is equal to VQ for all V an element of H10 space. Okay, so substituting the approximate solution obtained earlier in the more general form, that U be an element of S naught n space, which is the subset of H naught 1 space. So A of VU, which is equal to VQ. More explicitly substituting U and the V. Remember, we choose them to have the same base because the base functions are the same. And swapping summations and integrals, we obtain this solution, this form, that Ck A of pi j pi k, which is equal to pi j q for j1 to n. So connection to the physical system. So mechanical formulation, that strain energy, external work, the potential energy. So this is actually minimization method. So mathematical formulation, what we have discussed yet. So let us take the initial value problem with constant coefficients. For example, minus p of u prime, this second order differential equation in terms of u plus zu, which is equal to q of x in the interval of 0 to 1, and p and z, which are greater than or equal to 0, and the boundaries are u0, which is equal to u1 is equal to 0. As a first step, let us divide the domain into n number of subintervals with the following. So that x naught is given 0, that x naught is equal to 0, x1, x2, x3, xn is equal to 1 because our interval is from 0 to 1. So x naught is at 0, and the xn is at 1. So each subintervals like xj minus 1 and xj, as j is equal to 1, to n is called the finite element. So how we can represent the trial base function? Look, x naught, xj minus 1. Here there is xj plus 1, and xn. Okay, these are the trial functions. So how we can define the pi function? Pi of j of x is equals to, these are shaped functions actually, x minus xj minus 1 over xj minus xj minus 1 for xj minus 1 less than or equal to x less than or equal to xj. So for this interval, especially for this line, we are defining for this interval from xj to j minus 1 to xj. And next, from xj to xj plus 1, we define another shape function, xj plus 1 minus x over xj plus 1 minus xg. This is the shape function we define for this line. What we are defining is for this line. This is also for the first case. For the remaining thing, we give it 0. For example, these lines are not defined here anywhere. It is not defined anywhere here, but it defines, for this one, we define this trial base. And for this one, we define this trial base. So with the base, the previous slide, we construct our approximate solution u of x. Look, u of x, and x is here. So for example, cj minus 1, cj plus 1, the same thing like this. It is almost the same. Again, pi j minus 1, pi j, okay? Our j is here. So for this domain, this is for this domain. For this case, okay? This is for this case, this one. Again, we can represent in terms of C. So this is the way how we can find the trial base function. So the problem at this point can be easily solved using the previous derived Galerkin method. So this is the formula which derived from the Galerkin method. A little more work is needed on this. So matrix form of the problem. Restricting u over the typical finite element, we can write u of x is equal to c of j minus 1, that this c are the shape function, pi j of x plus cj of pi j of x. For the, this is for the portion to the, in the interval of j minus 1 to j. Okay, x is an element of j minus 1 to xj, which in turn can be written. This interval, actually this interval, what we are talking is from here to here only. Okay, which in turn can be calculated as this. Okay, cj1, cj, pi j1 of x, pi j of x, which is equals to actually here they used interchangeably. Okay, and the v of x also. This d are the coefficients or the shape functions. In similar way, it also defined. Okay. So the derivative of u and the derivative of v, that trial function and the weighting function, derivative of them, we can find some relation. we represent this it in terms of H. Okay. So the variational formula can be element-wise defined as follows. So actually, by taking some example, we can easily understand what we are doing here. Okay. So this is the variational form of element-wise variational form. So substituting u, v, u prime and the v prime into those formula, we obtain this relation. Okay. So then finally, Kj, which is the element stiffness matrix, Kj is equal to P over H. This H represents the element length, actually. Individual element length is represented by H. Okay. From the very beginning, from here, this H implies element length, the J's element length. Okay. That means H is equal to xj minus xj minus 1. That means element length. So P over Hj with minus 1, 1, 1, minus 1 is the matrix for a particular element. Okay. So that will be assembled later. Okay. So the element mass matrix. Now, the element mass matrix also found as mg is equals to zhg over 6, 2, 1, 1, 2. This is the element matrix, mass matrix, and the external work integral. So the external work integral cannot be evaluated for every function q of x. So VQ, which is equals to an integral of Sj minus 1 for the element length. So actually here, what we are talking is the element length, Xj minus 1 to Xj, VQ dx. So this Q is the distributor load, V is the weighting fraction. So in the bilinear form VQ, we can calculate external work integral. So this Q is the load applied, the distributor load. We can consider linear interpolation of Q of x for simplicity. So let Q of x is equals to Qj minus 1, pi of j minus 1 of x plus Qj pi of j. This is for the element in between xj minus 1 to xj. Okay, yeah. It is an element of xj. So substituting the evaluation to the integral, we get this equation. Okay, so so now the remaining thing is assembling the domain. Once we consider one element, then we consider all the remaining elements as elements having the same properties, then we assemble this thing. So now, that assembly is the summation of A of J of for in the S domain. So dt kc. So C is equals to C1, C2, Cn. D is equal to D1, D2, Dn. So K is equal to P over H. H is the element length. So this is the assembly matrix of the stiffness matrix. These are all the matrices which what we have discussed yet. So system of linear equations. This is substituting the matrix form of the expression in this summation form. This summation implies that we are summing up all the elements into get the global solution. So by summing up, finally we obtain dt that k plus m of c minus I is equal to 0. So it's satisfied for all choice of D. Therefore, K plus M C minus I is equal to 0. I is this thing. Yeah, it is inertia, I think. This is mass, this is inertia. So let's take some practical examples, because this thing must be reinforced with some practical example, unless we cannot easily understand. So let's consider some heat conduction problem. So having a partial differential equation of the second order, this type, with the range of 0 to 1, or in the domain of 0 to 1, and the boundaries with the same boundary as we have discussed previously. So calculating this partial differential equation, just the homogeneous and the non-homogeneous part, finally, we can get this answer from the mathematics, that is from the linear algebra. We can find this answer, and the solution, the exact solution is given like this. So now we are going to find the finite element solution, not the exact solution. That exact solution may help us for the comparison of the result. So let's see. This is the problem type. So that is a heat conduction problem. At this age, at the left, there is a temperature of 20 degrees centigrade considered. And there are two materials are considered here. Bottom, heat coming in from the bottom, and this. To the right, insulated. Okay, here to the right, it is insulated. At the top, convection heat loss with H to infinity is considered. So this is the model. This is the problem. So what is T of X and Y? What is T of X, comma, Y? Now, the first thing is that discretizing the domain, as we have discussed, and taking the element and considering a proper shape function. A simple shape element is taken here. So let's consider 4 elements. Let the number of node n is equals to 5. Let the number of element be 4. So number of node is equals to number of element plus 1 in most cases. Okay, so let's consider the element length HE for all of the elements. Okay, so element 1, element 2, element 3, element 4. Node 1, 2, 3, 4, 5. So these are called global nodes. And when we are giving nodes for each of them 1, 1 to 1 to 1 to them, it's called local nodes. So this is a mesh of linear elements. So elements that are defined by 2 nodes only. Linear element means we have 2 nodes only. If it is quadratic, then 3 nodes, and so on. So this mesh is uniform. So the element length H is equal to 0.25. Why? Because the element, the general length is 1. So that when we discretize it into 4 equal parts, 0.25 is the length of element. So with the linear element, we'll obtain a piecewise linear solution. So let's see. U1 is equals to 0. We are now approximating the shape function. So U1 is equal to 0 because it is already given. U at x is equal to L is equal to 0. So that is U5 is equal to 0. These are known node values of nodes with known values. So U2, U3, U4 are to be found. So we have to determine this thing. So this is UH is approximate finite element solution. That UH means the hat function. Okay. So finite element solution is linear over each linear element. So it is a linear element. So the solution domain is C not continuous. It is C not continuous. It is continuous at element interface, but it is first derivative is not existing. C not means it has no first derivative. And the UJ is UJ prime, that is are nodal unknown values. The ultimate task is to calculate that. So U1, U1 and the U5 are already known, specified as essential boundary conditions. They are known, so their values are known. So UH, that is where now this is approximating the solution. So displacement function UH is equals to the summation of from J from 1 to NN. NN means number of nodes. UJ pi J. So this is now this satisfies if the following canonical delta property holds true. This canonical delta means 1 if I is equals to J, and 0 if I different from J. This is called canonical delta function. So the following approximations functions will work. Look here. For the first element, we have pi 1. Okay, this is the approximation function pi 1. For the second element, this and this will come. This is second element. For the third element means this element. Because there is node sharing at this point, that's why it takes this one. Here also node sharing are there, so this also comes for fourth element and for fifth element. So we generally represent it like this for the linear elements. Okay, pi 1, pi 2, okay, pi 3, pi 4, and pi 5. These are the approximation functions. These are Lagrange type approximation functions. They make sure that the solution is continuous across elements, but not it's the first derivative, that C not element. And they have a canonical delta property. So they have local support that is non-zero only over at most 2 elements. So this is also another representation. Okay, U2 pi 2, U3 pi 3, U4 pi 4. These are required things. U1 pi 1, U5 pi 5. These are known. Okay. Now, FEM use a weak form of differential equation, same as that of Ricci's function. So U is used instead of U hat for clarity. So the residual R is equals to minus of this. This is actually the given solution, no solution, but the partial differential equations, and which is represented in terms of residual R. Okay. So R is equals to, this is the part of the equation which is equals with 0. Let me go back and show you. So this is the equation. And this minus x squared come to here and residual. So this is the hat function. Sorry. So R is equals to, this is then multiplying it is the weighting function W. then which is equals to 0, which implies that after performing integration by part, okay, we multiply the equation. This R is equals to directly this thing. Substitute in place of R this thing. Okay, W, multiply it with W. Okay, W times D square U dx squared minus WU plus WX squared dx, which is equal to 0. That is residual of error is equal to 0. The meaning here, residual is error. So after integrate, we can get dw dx, du dx minus w du dx at 0 to 1. Then finally we get the weak form. This is a solvable or a very comfortable form of the equation. That is a weak form of equation. So once we get the weak form of equation like this, equation like this, the weak form of equation, then we can solve it for each of the interval. Okay, for wi is equals to pi I, that I is equals to 1, 2, 2, 5 in our case. This nn is equals to 5. So that we need 5 equations. From this equation, we are going to develop 5 equations, okay, for each interval. So in every interval, there is size, that psi1, psi2, that pi1, pi2, pi3, pi4, 5. That are the shape functions or the functions. So we substitute in terms of the weighting function, we substitute the shape functions. Okay, these are the substitutes. For the first, W is equal to pi1, W is equal to pi2, W is equal to pi3, W is equal to pi4, W is equal to pi5. By substituting this, we can get 5 equations, okay, in each, in the above equations. So the integrals are easier to evaluate over each element separately, and integrals are non-zero only over certain elements, because pi1 works only in element 1, but pi2 works in element 1 and element 2. It will not go. So, for example, if we take third equations from here, this third equation, if we take this equation and call it as I3, okay. So that d pi 3 du dx, d pi 3 over dx times du dx minus pi 3u plus pi 3x squared dx. So which is non-zero only over element 2 and element 3 only. Because pi 3 is non-zero only over E2 and E3. You can see this thing. What does it mean? This is pi 3. So this pi 3 non-zero for element 1 and element 3 only. It cannot go for element 1. For element 1, it is 0. Okay. For element 2 and for element 3, it works. It is non-zero value. But the remaining, here it is 0, Here it is 0. So, okay, so let's take pi 3 as the integral of, because that the whole equation, bring whole equation, and take it as w is equal to pi 3, as w is equal to pi 3. For domain in element 2, this is element 2 domain and element 3 domain. That means let's go back. Okay. For element 2 domain, we define some form of equation for this. Sorry. Yeah, here we define, okay, in the element 2 region, it is 4x minus 1. This pi 3 is this one. This pi 3 is defined as 4x minus 1 in the element 2 region. And in the element 3 region, pi 3 itself is 3 minus 4x. Okay, so pi 3 has two definitions at this at element level. So in domain 2, it is 4x minus 1. In domain 3, it is 3 minus 4x. So we can substitute pi 3 in this example, pi 3 in two different regions. Okay, this cancelled. We have left this equation. That is this one. So for the first case, and for the second and third case, we substitute the pi 3 values here. Okay, this is for 3, this is for 2. Finally, we can solve this thing using Matlab. Okay, so I will try to model it or introduce it with Matlab in the next or sometimes, but I simply show you the Matlab program for this equation, because in most of large matrices, we use Matlab because that calculating using hand calculation is very tedious. So this is the Matlab program for finding I3. I3 means equation number 3. So this is simple. I don't want to say anything on the Matlab program now, but after calculating in Matlab, we can get this equation from I3 that is relating U to U3 and the U4. In I3, it relates the displacement function U3. No, look, this pi 3 means here we have U2, here we have U3, and here we have U4. So it relates this three displacement functions so that you can easily observe it from this. So 97/24 minus of U2 plus 47/6 U3 minus 97/24 U4 plus 25/384. That is the result of I3 from our Matlab calculation. So, okay, then the resultant of 5 equations. Finally, for all the 5 equations, we actually I have all the Matlab program for all 5 equations. I can show you the Matlab program here. It is already there. This is the Matlab program for the overall system. So this is K matrix. This is U matrix, U1, U2, U3, U4, U5. These are nodal displacements. These are the stiffness matrix. That is 5 by 5. No, 5 by, yeah, 5 by 5 matrix. And these are the external, the force matrix. And this is the external force matrix. So K is stiffness, that is n by n matrix. U is nodal non-vector, that is nodal vectors, n by 1 matrix. Force is n by 1 vector, force vector, and boundary term vectors. Q are boundary term vectors. In our case, yeah, these are, that is n by 1 matrix. This system has 5 equations for 5 unknowns. So U1 and the U5 are already known. So that will simplify our work. If we know U1 and U5, we can leave that portion of the solution. So look, we consider only this portion. If U1 is 0, U5 is 0. So if I multiply this thing by U1, it is 0. So we can leave that part. And there is an effect of this thing. So that will come here. Okay. And there is an effect of this one and this one. So they are considered here. So we consider that this portion of the matrix with this, only the red color part. And the blue color part will be come to the force effect here. Okay. Okay. This reduces the system to 3 to 3 matrix, and that's kind of noting out the known parameters. And the reduced system for the problem is like this. Actually, still it is related with U1, 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 U5, U5. So they are for 0. This will be still 0. Okay. So we have left F2, F3, F4, Q2, Q3, Q4. So finally, there is no Q or boundary terms in our case. So they are 0. Finally, we can find U2, U3, and U4. Okay, this is the finite element solution. This is FEM solution. FEM solution. And this is exact solution from the linear algebra or from the mathematics. Exact solution, finite element solution. Okay. So this is a simple Matlab program for the particular example. And this is the comparison of the exact solution with FEM solution. So the blue color one is the FEM solution. And the red one is the exact solution from the. So as we see, there is a variation in the results. Okay. So if the discretization size is much smaller, that maybe more than 5, no, more than 4 elements. For example, if it is 8, quite sure it will come to somewhere here and almost the same. But what we have discretized is for 4 elements. That means element 1, element 2, element 3, element 4, so that the solution is kind of having a small error. That is, so this is what people, and then we can calculate for external loads or boundary loads case. Actually, that is further we can discuss on those issues. So thank you very much. This is sufficient for today. We'll continue with some simple problems in the next. And also I will try to use Matlab as well as the FEM softwares like ANSYS and Abacus. If anyone interested, please tell me and I can do it for you. So this is what